All right, well, good Wednesday morning to everybody. Plan today is to keep going where we left off. We're going to talk partial fractions. I think we're going to spend quite a bit of time on this because my sense from last time is that a lot of you have never seen the algebra involved in partial fractions. And if we don't understand the algebra, uh, then we're sunk, because that's the whole point of this, is doing the algebra to make it so that our integration is easy. So we'll spend quite a bit of time looking at these examples and talking about the process, because I want you to feel comfortable with it, because it's a really useful thing when you've got these forms. So that's my plan. But as always, I'm open to helping you guys with any kind of homework questions. Is there anything you guys want to look at from previous sections? All right, so from 3-3, we have a vote for number 12 and number 6, maybe. All right, well, maybe I'll do number 6. Maybe we'll look at it. Thanks for that, Alexi. All right, I'm going to go ahead and jump over then. We'll go look at 3.3. If other stuff comes up, please just let me know. But let's head on over there. All right, so number 12 was a for sure. And then number 6 was a maybe. Okay, so let's look at number 12. So it says use integration and trig substitution to find the area enclosed by the ellipse. Oh yeah, check this out. We're going to actually be able to find the area of an ellipse now. No, you're not excited? It's good stuff. It's good stuff. Okay, so if we're going to do this, think about what we do to calculate area. We know that we can use integrals. I mean, that's the first thing we learned with integrals. So let's take this guy and let's draw its picture and think about how we're going to set this up to do integrals. So I'm going to go ahead and jump over to the whiteboard. So let's just start. We got our equation is x squared over 9 plus y squared over 16 is equal to 1. So I'm going to start with a picture of it. So this is an ellipse that goes left and right 3 and up and down 4, centered at the origin, right?
Go ahead, virtual dispatch.
We're not subtracting anything from the x's and the y's, right? So that means we're centered at the origin. So we're going to go left and right 3 and up and down 4. So it looks something like this, right? So that's 3 minus 3 minus 4 and 4. All right, so if we're going to try this with just good old plain integration, the rectangles that we're going to add up are going to be these kind of rectangles, right? So this is one of those where we need top minus bottom. So we should figure out what the equations of those functions are, and we'll do that by solving this guy for y. Right? If we can get y equals, then we'll have that value. So I'm going to get rid of the fractions first by multiplying by 144. So I get 16x squared plus 9y squared equals 144. 9y squared equals 144 minus 16x squared. Divide by 9. Let's see, that's 16 minus 16/9 x squared. And then I'll take a square root. Okay, so that's where we are once we get y equals. All right, any questions at this point? Okay. So the top is the positive square root, and the bottom is the negative square root. Okay, so the top side here is the positive square root of this stuff. And then the bottom is the negative square root. So if I do top minus bottom, subtracting the negative is the same as adding. So I actually have two of those things. So I'm going to get that area by integrating from -3 to 3, the function 2 square roots of 16 minus 16/9 x squared dx. All right, so before I move on, before we even attack this calculus, I want to make sure we're all good with the algebra that I did and the process I'm doing. So any questions at this point? You feel okay? All right, so here's where we are. And so now let's go ahead and take care of this integral. I'm going to help ourselves out just a little bit. I'm going to factor out the 16 from inside that square root. That's going to come out as a 4. 4 times 2 is 8, so I'm even going to pull that out front of the integral. So I have 8 integrals of -3 to 3 of the square root of 1 minus x squared over 9 dx. All right, so now comes the u sub, or the trig sub, I mean. So if you look at our form, we've got a square root of a difference of squares. That's what should trigger trig sub. I mean, I know that this question said use trig sub, but that's the form that makes you go, ooh, trig sub. I've got a square root with a sum or difference of squares. So then the question is, which one do we do? So which trig sub are we going to use? Are we going to use sine, tangent, or secant? What does that form suggest? All right, good, Alexi. It's going to be sine. And we're not going to have x equals. We're going to have x over 3 equals sine of theta. And I'm using x over 3 because that's what's being squared here to get me this. So I'm really using x equals 3 sine theta. That's what would have happened if we had multiplied that 9 through. Then it would have been 9 minus x squared. And I think when we first built it, we saw it as the square root of u squared minus, or a squared minus x squared. So x is equal to a sine theta. But we're going to use x equals 3 sine theta. So dx is going to be 3 cosine of theta. So let's see what this gives us. All right, so for our integral, we're going to have the square root of 1 minus sine squared. And then the dx is a 3 times cosine theta, d theta. So there's the change in the integral when we go here. I'm not going to worry about the bounds and the 8 for right now. I'm just looking at the thing that we have to integrate. So the 1 minus sine squared is a cosine squared. Its square root is cosine. So this is actually the same as the integral of 3 cosine squared. All right, so that's what this thing turns into when we do the trig sub. All right, so how are we doing at this point? So far, so good. I will take silence as we're good. All right, so then cosine squared, we're gonna have to use an identity to help us with that one. Pull the 3 out front. That's the same as 1 plus cosine of 2 theta over 2. And that we're going to be able to integrate. All right, so let me come back over here, erase some stuff so we can finish this guy off. All right, so that's 3/2 times theta plus 1/2 sine of 2 theta is the integral of this thing. Right, so the 3/2, hopefully you see that the 3, right, that came from the 3 out front, and then the half on the bottom. The 1 becomes a theta, and then the cosine of 2 theta, when you integrate that, becomes 1/2 sine of 2 theta. All right, so that was the integral of this thing. We're going to have to put back in that, replace the theta with x's and all that good stuff. So we're going to do one more step of identities. We use the double angle identity on sine. And that's 2 sine theta cosine theta. So the 1/2 and the 2 cancel, and we're left with that. Okay, so all this that's in blue was just the integral. It didn't have the bounds or anything. So let's replace back so that we can evaluate with our bounds. So we're going to have 8 times 3/2 times. So I'm going to need theta, and then I'm going to need sine theta and cosine theta. All right, well, to get the theta, if we come back over here to our substitution, use inverse sine. We're going to get the theta is the inverse sine of x over 3. Sine of theta, we already know, is x over 3. But then we need cosine of theta. So let's draw a right triangle. That guy's our theta. We know sine is x over 3. We need cosine. So I'm going to use Pythagorean theorem. And that makes this side the square root of 9 minus x squared. So then the cosine of that angle is square root of 9 minus x squared over 3. And we're going to be evaluating that at 3 and minus 3. Whew. All right, so check this sucker out. This guy right here, all this, that was this integral over here. So, I mean, it didn't look that ugly, right? I mean, yeah, it was a square root of some stuff, but this is actually what the antiderivative of that sucker is. Whew. All right. Well, now we'll plug in our 3 and our minus 3 and see what we get. So we're going to have 8 times 3/2 times. When I plug in 3, I get inverse sine of 1. Over here, notice when I plug in 3, the 9 minus x squared becomes a 0. I get nothing. So that's what I get when I plug in 3. When I plug in minus 3, I get 3/2 times the inverse sine of minus 1. And again, that thing's equal to 0. So if I pull out the 3/2, that's 12 times the inverse sine of 1. Well, if you think about what angle gives us a sine of 1, that's pi over 2. And then what angle gives us a sine of -1, that's another negative pi over 2. So pi over 2 minus a negative pi over 2 is pi over 2 plus pi over 2, which is pi. And there we go. There's the area of that ellipse. So, yay, we can find the areas of ellipses now? Well, yeah, it is yay. And it turns out if we were to do this generically, I'll show you what the formula is for the area of an ellipse. If you did it generically instead of this one, you know how we had specific values? We had the 9 and the 16. If you had left those as a squared and b squared, you could have done the same thing, had a's and b's in here, and you would have ended up with a generic formula. But before I show you that, questions on this? I know you've got them. Where did I lose you? What steps are we unsure of?
Actually, I mean, I have a question. I feel like you've kind of clarified it on this situation. On Monday, you took the derivative of a 1 or a 1/2, or the integral of 1/2, the antiderivative, and you kept it as 1/2. But in this situation, you turned it into a theta, and so I'm just going to guess that you are supposed to add the theta, right? Because you're going backwards and you're.
If you integrate a constant, there should be a theta on it. If I didn't last time, it was just a brain fart. But anytime you have a constant and you integrate the constant, you get that number times the variable, right? Whether it's an x or a theta or whatever. Yep.
Thank you. Yeah.
Yeah, you're welcome. Okay, now I do want to show you one thing that could have made this a little bit faster. And that's the whole trick of when you do the substitution, you change the bounds at the same time, right? So remember how I said, well, I'm not going to worry about the bounds. I'm just going to leave them. And then we replaced, because this thing ended up getting kind of like, not kind of, it definitely got ugly. We could have saved ourselves a little bit probably had we done the substitution on the bounds as well, right? So like think about this, when x is equal to 3, if I plug that in here, I get 1 equals sine of theta, which gives me theta equals pi over 2. So I could have put that in as my bound here. And then the same thing, if x is equal to -3, then we get -1 equals sine of theta. So that's theta equals minus pi over 2. And so if I had put those bounds in, that means at this point, actually, I need the 8. I dropped the 8 out front. Because remember, we had the 8 that was out at the very beginning. So if I were to put that 8 back on here, then I would have been done. And watch how fast this is in terms of evaluation. So we don't have to put in, first of all, we don't have to solve for theta. We also don't have to solve for cosine of theta. We don't even have to have that little right triangle. And instead, this would have been, so 8 times 3/2, again, that's 12, times pi over 2 plus sine of pi over 2 cosine of pi over 2 minus negative pi over 2 Oh, whoops. Hold on a second. Premature parentheses there. Minus pi over 2 plus sine of minus pi over 2 cosine of pi over 2. And for these, the cosine of pi over 2 and cosine of minus pi over 2 are both 0. So we're left with 12 times pi over 2 minus a negative pi over 2, which was where we ended up being anyway. So we get 12 pi. So I highly recommend, if you're doing a definite integral, so you've got bounds. If you're doing a definite integral and you do trig sub, plug them in and change the bounds, because then you might not even have to draw the triangle to replace all the other little pieces. All right, so there you go. There's the area of that ellipse. It's 12 pi. But like I said, if you did this generically, sort of clear all this, we'll make room for a little picture. All right, so if you do this generically on an ellipse, so let's say here's our ellipse, and this ellipse is given by x squared over a squared plus y squared over b squared equals 1. So a and b, just to remind you if you don't remember this, a and b, a is the distance from the center out right or left, and then b is your distance from the center up or down. Turns out that the area is always a times b times pi. And so for hours, you may remember that it went left and right 3 and up and down 4. So 3 times 4 is 12 times pi is 12 pi. So before you start going, well, I wish you'd just given us this formula, because then we could have just done, well, where's this formula come from? It comes from the calculus. So we could have derived that first. I think you would have hated it. Think about all this trig sub stuff, but with A's and B's in there instead of, 3's and 8's and things like that. You'd have hated it. But if we had followed that all the way with A's and B's, we'd get this formula. So kind of fun fact. And then think about this. Think about a circle. A circle, it's really an ellipse where A and B are the same, right? We call that the radius. Well, if those are the same, pi r squared. Yeah, I know nobody cares. But yeah, there you go. Beauty of calculus. That's where a lot of these formulas come from, by the way. The things that you learned for geometry comes from doing calc. All right, so good for this one. I'm glad Alexi said it. This one, it makes sense now. Yeah, Rigny, I agree. The more you learn calculus, the more you see how useful it is and the power that it has. Just wait until you do an entire year of calc. Like once you're done with the sequence, we'll be doing things in the fourth quarter in vector calculus, and all of a sudden you'll go, oh my God, now I totally understand why all those things happened in the early days. I mean, it is kind of fun that it gets comes back around. All right, so I know that there was the 6 maybe. Let's go take a look at 6 and just see what we're gonna do for this one. All right, so for this guy, starts with the, okay, so which trig sub is gonna be correct for this integral? So let's look at it. First of all, what tells you you're gonna wanna use trig sub? We have a square root of a difference of squares. Okay, so that immediately keys us in. So then the question is, which trig sub do we use? Well, it's a difference of squares, so we know that's either sine or secant. Since our variable is first, since the variable is positive, that tells us we want secant. And then which one do we want? Well, this is a u squared minus a squared. So the u is 9x. So we're going to let 9x equal 5 secant of theta. So if we solve that for x, it would be x equals 5/9 secant. So then what does that thing look like once we do that substitution? Well, let's go get that set up. I'm just writing down real quick what this thing looks like. All right, so let's go to the whiteboard. We'll get rid of all this garbage. We'll start with fresh garbage. All right, so we have the square root of 81 x squared minus 25 over x cubed dx. And again, we're going with the substitution. 9x equals 5 secant of theta, or x is 5/9 secant of theta. So dx then is going to be 5/9 secant tangent d theta. So let's see what we get once we plug everything in. So we're going to get the square root of 25 secant squared minus 25 over 125 over 729 secant cubed. That's that 5/9 secant cubed. And then dx, we're going to 5/9 secant tangent. And there's all kinds of simplification that's going to happen here. All right, so let's see, the square root of 25 secant squared, 25 comes out as a 5. Secant squared minus 1 is a tangent squared, so the square root of that is tangent. So this is 5 tangent times 5 secant tangent divided by, well, if I put that 9 in here, that becomes 125 over 81 secant cubed. All right, so we can simplify some more. That's going to end up being 81 over 5. As I flip that thing over, the 5's cancel. One of those secants goes away, so I'm left with a tangent squared over secant squared. And then check this out. So tangent is sine over cosine. Secant is 1 over cosine. Those things, when I do the division on that, right, flip this thing over and multiply, that's just equal to sine of theta. So this then, since that's tangent over secant squared, this ends up being the integral of 81/5 sine squared. All right, so that's what we're going to integrate. Obviously, we want to change that into the using the trig or the power reduction. Turn that into the 1/2. So this is going to be 81/10 integral of 1 minus cosine of 2 theta d theta. And then you're good to go. So I think I'm going to leave it at this point. But when it comes back to it, when we have to substitute in, the other thing I'm going to show you real quick is just what the triangle looks like. We have here, if you were to solve this for secant of theta is 9x over 5, which means cosine is 5 over 9x. So there are those two sides. And then you'd use the Pythagorean theorem on this third side. And you get that that's 81x squared minus 25 inside of the square root. So now you've got this for whether it's sine or cosine or tangent or secant, whatever you're going to replace, you can now use those sides.
I have a really quick question on the
Sure.
first box in the where you're inputting it. So that's the one I literally have gotten wrong on all of these. I don't know if I'm like simplifying too much before. Like I know the multiple choice which one, but like the box after that. Can you explain which one would go into that one?
Yeah, well, let me come back. Let's see what we got here. Okay, so which integral do you get after substituting for x? At this point, I would probably put in the, pardon me if I don't remember the exact numbers, but it was like 81/5 sine squared theta. I think that's what I would put in here. And this could be one of those things where the computer is not smart enough to recognize all the various different forms. Because with Trig, as you know, with all the identities, you can, change them like crazy. But that's what I would put in. I'd put in the, after we had simplified all the secants and tangents and everything, but before the double angle step. Does that make sense? Let me jump back and show you. So I would put in this one right here. So again, is that going to be good? Is it going to accept that as an answer? I don't know, right? Computers are great, but they're dumb. I mean, they're not smart enough to recognize sometimes all the various things that can happen. And it's probably good that they're dumb, because then otherwise Skynet happens and we don't need that. So anyway, if you end up having trouble, if you're like, man, I know I've got to be doing this right, but it's not accepting it, let me know and I'll look at your specific one and I can give you the points on it if you are putting in a proper form. I mean, I guess technically you could put in this form into that box and it should give you full credit. But, well, A, you don't want to have to type this in. And it might not actually give you full credit, but technically, yeah, that's what you get after you do the substitution. I mean, it just turns out there is a much simpler form, but anyway. All right, so we cool with trig sub? Okay, that's wrong question to ask, because nobody's cool with trig sub really until they've done a billion of them. But hopefully at least you're seeing the process. Actually, one more thing I meant to point out, I didn't think about before I shut down my screen. Let me pull it back up. I don't know if you've noticed this, and this usually requires doing quite a few of these to notice it. But when you come back to the right triangle and you start with your two sides, you find your third side. That third side always has the square root that was in your original integral. That's a good little check, by the way, just to make sure that your picture is looking right. If you end up getting something that's not what was in your original integral or equivalent to it after some sort of reduction, you're doing it wrong. So just fun fact, that always manifests itself back somewhere in that right triangle. Anyway. All right. So Give me a second here. I'm going to hop up to the whiteboard and we're going to do some more partial fractions. So strap in, get ready for algebra. But trust me, the algebra is huge because it makes the calculus that much easier. All right, so I'll be right back with you. All right, so partial fractions. As we saw last time, there's a recipe to this. You take your fraction, you factor the bottom. You then split your fraction up so that it has bottoms that are all those factors. If they're repeated factors, they show up multiple times, as many times as the power. If they're linear factors, right, just 2x minus 1, things like that, they get a constant on top. If they're quadratic factors, I haven't shown you any of those yet, but I'll show you one with the first one we do today. If they're quadratic factors, they get a linear on top. Okay, but anyway, so we break it apart, then we put them back together. We add it, and then we combine everything on top, and we set those tops equal to each other, and then we create our system of equations by a couple different options. I suggest plugging numbers in. Once we get that system of equations, we can solve it and figure out all the variables, which then tells us how that fraction breaks up. So then we can take that broken apart fraction, we can integrate it. And I know just that, a little recap, already is hurting your brain as making you go, oh my Lord. Right? But yeah, there's a ton of steps here, but it's very procedural. Always the same thing every time. So those are good because the more you practice them, the easier they get. It's muscle memory. You guys know that, right? Know about muscle memory. If you played sports ever, you know muscle memory, right? That you can walk up to the foul line, shoot the basket. You don't even think about it. You just do it because you've done it hundreds of times. Well, this is no different. It's this muscle that we're working, and we're training it how to do partial fraction. All right, so we're going to start with this one as our first guy for today. Again, it doesn't look terrible as an integral. And it really, I mean, it's not terrible. But we're going to look at 1 over x to the 4th minus 1. Okay, so that's the one that we're going to integrate. So it doesn't seem that bad. And it really isn't. Its integral is going to be pretty easy. However, we're going to have to do quite a bit of algebra to get there. All right, so here we go. Let's start by factoring this denominator. So x to the 4th minus 1. Hopefully you recognize that that's a difference of squares. So that factors to x squared minus 1 times x squared plus 1. But this one we can factor a bit further because x squared minus 1 is also a difference of squares. So there's the factoring for this denominator. That's always step number 1. Factor your denominator. The x squared plus 1 we can't factor down any further. It's a sum of squares. Well, okay. You guys are far enough advanced that I can actually say this now. I like when I get to calculus, I start giving all kinds of yeah, but like you were taught, you can't factor that, right? X squared plus 1, you can't factor it. Well, you can factor it if you allow yourself to factor over complex numbers. Just FYI. So But we can't factor it over the real numbers, so we will leave it like this. And we're going to stay in the real world because we're doing calculus. I'm just saying later, if you go further on in math, you start doing stuff with imaginary world, and yeah, factoring that's not a big deal. It's x plus I, x minus I. Just smile and nod. All right, so here are the factors. So what we're going to do is we're going to take this fraction, 1 over x to the fourth minus 1, and we're going to split it into 3 pieces. And each of those pieces is going to have one of those factors as the denominator. There aren't any repeated factors, right? It's not like there's a square or a cube or anything like that on any of the factors, so we don't have to have repeats of them. So these 3 factors are going to lead to these 3 fractions. And now what we're going to do is we're going to put the generic things on top. So x minus 1 is linear. So on top, it gets a constant. X plus 1, also linear. So it also gets a constant, but I'm going to give it a different number or a different name because they might be different. And then the x squared plus 1, since that's a quadratic, on top, it's going to get a linear top, because there's the possibility that that is linear. So that's what 1 over x to the fourth minus 1 is going to look like when we break it apart. It's going to have those 3 fractions. Okay, so let's just pause for a second. I want to make sure everybody's good with what I did. All right, so after I factored, break it into mini fractions, and then depending on what the factor is, tells me what goes on. All right, so we factored, then we split it apart. So now the next step is put it back together. So if I were to combine these 3 into one fraction, what I'd have to do is multiply the tops by the missing factors. So that's what this is going to look like. We're going to have a times x plus 1 times x squared plus 1. I need more space. Hold on. A times x plus 1 times x squared plus 1. So the a is missing those 2 factors. The b can have an x minus 1 times an x squared plus 1, because that's missing those 2 factors. And then lastly, I still don't have enough space. A times x plus 1 times x squared plus 1 plus b times x minus 1 times x squared plus 1 plus, okay, then our cx plus d is going to be multiplied by x minus 1 and x plus 1. So all of this that's in purple, that's the top of the fraction once we put it together. And what I know is that when I put it together, that top has to equal 1. Because that's what this fraction's top originally was. Okay, so that's the put it back together. And now we're going to figure out what A, B, C, and D are by plugging in numbers for x. We're going to plug in numbers for x. And we're going to set that, whatever this thing is, when we plug those x values in, equal to the top of the other fraction. All right, so I have a bunch of choices for what I'm going to plug in for x, but I'm going to start with x equals 1. And I'm choosing x equals 1 because it's the 0 of the first polynomial, the first factor. And watch what happens when I plug in 1. So I'm going to get a times 2 times 2, right? A times 2 times 2. And then I'm going to get, I'm going to go ahead and write this one out. I'm going to get b times 0 times 1. And then I'm going to get plus c plus d times 0 times 1. Or sorry, not 1. Okay, so I just plugged in x equal 1. And what I know is that has to equal the top on the other side, which is 1. All right, well, I get 1 equals 4a, and then I get b times 0, c plus d times 0, everything else is gone. So by choosing something that makes these factors 0, makes it so that it's a really easy thing to solve. So I actually already know a. A is 1/4. Boom, I got one of my values. All right, so now let's do the same thing with -1. Because -1 makes the second factor 0. So now everything that has an x plus 1 is going to go away. So I'm going to get 1 equals no a's. I'm going to get b times -2 times +2. And then the cx plus d stuff, again, it all goes away. So I have 1 equals -4b, which gives me b equals -1/4. Cool. So I've got a and b. But now my good choices for x are gone, because x squared plus 1 never equals 0. Well, with a real number. So I have to pick something else to plug in for x. In fact, I have to pick 2 more things to plug in for x, because I still have 2 variables I don't know. But I get to choose whatever I want. So I think a really good third choice is going to be 0. I like plugging in 0. 0 is easy to do. So let's try x equals 0. All right, well, if we let x equal 0, that's going to give us a times, well, so 1 equals a times 1 times 1, that's a. And then I'm going to get b times -1 times 1. So that's minus b. The cx, well, if x is 0, c goes away. So I get d times -1 times +1, which is a -1d. So d is going to equal a minus b minus 1. Well, luckily I know a and b. Right? I just calculated those, so I can plug those in. So I'm going to get 1/4 minus -1/4 minus 1. That's a half minus 1, which is -1/2. All right, so that one required a little bit more work, but we're able to get it. So we've got A, we've got B, and we've got D. So lastly, we got to get C. We got to plug something else in. Well, I've already used all the numbers I like. Well, really, I like plugging in 0 and 1. But I've used 0, I've used 1, I've used -1. So I got to pick something else.
Can you pick a fraction?
I can pick a fraction.
But would that make it more complicated in our case?
I think so.
Okay.
Hell, if
I was
you
going to
want,
say 2. I was going to say 2, but I thought it might be a fraction.
No, I like 2. Let's do 2. I think 2 won't be bad because at least like the x minus ones, those are just going to turn into 1, and so that might not be terrible. So yeah, I would probably choose x equals 2.
Bruce, if you have all, sorry.
No, go ahead.
If you have all three, or if you have A, B, and D at this point, can't you just plug them in to figure out C? Because it has to equal 1, I thought.
Okay, well, if I were to do that, I'm still going to have C's as I expand out. And what the C value is.
Oh, right, because there's an X.
What's that?
I didn't realize there's an X still. I think that's why you have to plug in.
Yeah.
I see now. All right.
So, but you could do that. You could plug in your A, B, and D, but there's still going to be C's left over in that polynomial. So there's going to be something that you have to solve. And
yeah, there's still something missing.
Distributing it all out, I'd rather just plug in a number. So no, you're always going to have to plug, if you do this technique, you're always going to have to plug in as many numbers as unknowns that we have from our decomposition. So unfortunately, there isn't a shortcut. All right, so let's plug in the 2. So we're going to get 1 equals, right? 1 equals. Plugging in 2, I'm going to get 3 times 5 times A, so 15A. I'm going to get 1 times 5 times B, so 5B. And I'm going to get 2C plus D, 2C plus D, times 1 times 3, so times 3. So we have 1 equals 15A plus 5B plus 6C plus 3D. But now, since we know A, B, and D, we can put those in. So we're going to get 1 equals 15 fourths minus 5 fourths plus 6C minus 3 halves. All right, so let's simplify this sucker. 15 fourths minus 5 fourths is 10 fourths, also known as 5 halves. 5 halves minus 3 halves is 2 halves, also known as 1. So 1 equals 6C plus 1, which tells us that 6C equals 0, which gives us C equals 0. Okay, cool. So we now know the 4 values for the pieces of our decomposition. All right, but this is actually good news because now I can put those in for my A, B, C, and D. And this is what my integral now looks like. So I apologize, I have to erase some of this stuff. This is where I really wish we were in the classroom, right? And for those of you who know the college, this is actually where I want to be up in A208. That's the really big one upstairs. It's got the whiteboard like all the way across the screen. That's also like 20 feet tall. Then I might be able to do all of one problem on one whiteboard. This is what you're going to find. You're going to like do an entire page of paper. Like you might be at an entire page already, and we're not even done yet. Right? This is, I mean, there's a ton here. All right, well, here's where we are.
Hang on, she lost me there for a second. Wouldn't they be negative or minus 5B and minus the C and D? Because, or did I got lost there? Sorry, yeah, you just erased it all, but But you know what? Yeah. Well, if you put in 2 for the b x minus 1, wouldn't that make it a -1? Then you times it by the 5, so wouldn't that be minus 5b?
So I put in 2.
Yeah, and then it's x minus 1, so that's a -1. Oh no, that's a
No,
1. Never mind. I'm going backwards. Brain fart. I apologize.
I think we're good.
No, you were good. I see it now. I apologize.
Okay. No, you're all good. All right, so here's where we are then. We had originally we were looking at x to the 4th minus 1, right? But now this is what we're going to get. So we have a over x minus 1. That's going to be 1/4 over x minus 1 plus b over x minus 1, or sorry, x plus 1. So minus 1/4 over x plus 1. We have c times x, so 0, plus d minus 1/2 over x squared plus 1. Now, I know you're not used to seeing fractions on top, and we'll simplify it. I just wanted to show you exactly how that plays out with those numbers. And so if we make this look more like what you like, this is 1/4 times 1 over x minus 1 minus 1/4 times 1 over x plus 1 minus 1/2 times 1 over x squared plus 1. All right. So, ready for good news, bad news? I'll give you the bad news first. We like the bad news. Bad news is we're not done. Good news, but we're done with the algebra. All right, we're done with algebra. No more algebra to do. Now we're ready to do the calculus. Because remember what we were doing is we were integrating 1 over x to the 4th minus 1. Okay, well, that means I'm integrating this thing. I have 3 pieces, so I have to integrate each one separately. But watch how fast this is. The 1/4, that's a constant multiple. 1 over x minus 1. Hopefully you guys all recognize that form. What's that integral going to give us?
Is it sine?
Not that,
Oh,
but it is a nice function. I think it's 1 over u. What do we get when we integrate 1 over u? There you go, natural log. So this is going to be the natural log of x minus 1. I'll even be good for once in my life. I'll even give you the absolute values. So this is the natural log of x minus 1. All right, so the next piece, we got a minus 1/4. 1 over x plus 1. That's also a natural log. The natural log of x plus 1. All right, so then we get to the next piece. We got a minus 1/2. And what do we get when we integrate 1 over x squared plus 1? All right, close, Bruno. It's not tangent, but inverse tangent. So that guy's the inverse tangent of x. And then, of course, we put on our plus c. All right, so remember sweet little cute 1 over x to the 4th minus 1? Well, that is its antiderivative. Not so sweet, not so cute anymore. All right, but think like a mathematician. Yes, we got it. We got the integral. It required a lot, but we got it. We figured out its antiderivative. And also notice how easy the calculus was. This calculus was fast. It's crazy fast. The bulk of the work was in the algebra. And no lie, everyone hates partial fractions. Everybody. So when you're, I mean, hate might be a strong word, but I think for some of you that's maybe even a soft word right now. But we have intense dislike for this because of all of the work we have to do. Tons of steps, right? We just want to be done. Unfortunately, this is there's a lot of work, but the algebra stuff, I mean, you really do have to think about this the way math is. Like algebra, especially when calculus was brand new, algebra was known. Algebra is no big deal. And it really isn't a big deal. I know we hate it in our modern world. We hate algebra. But algebra is easy. It really is. If you think about the steps that you have to do, partial fractions isn't hard. It's tedious, right? It's tedious. It takes a lot of time. Hold on, I got it. If this shows up on the exam, will there be several to be a nightmare scenario? First of all, if this shows up on an exam, when this shows up on an, because there will be something where you have to use partial fractions. First of all, just realize that I'm not going to put more than one of them on an exam, because I already know that one of them can take like 15, 20 minutes itself. Right? So you have to be aware, I'm aware of that. Also be aware that because I know that they take forever, I tend to give you ones that are not horrible, hopefully, in terms of their structure and how long it takes to do. But I would never give you more than one on a timed exam. Oh, good Lord. All right, so something that was seemingly easy, right? No big deal, it's just 4 plus 1. Still took us a while, but we got it. We got its antiderivative. I will also tell you that if you were to put this into something like Desmos, Symbolab, UT89, it's very likely that you get a form that doesn't look like this, because it will do things like the rules of logs. It'll combine these two into a division, and then maybe bring that 1/4 in, and or if there's trig stuff, it'll do identities. So I just want you to be very aware that if you use that kind of stuff to check yourself, realize that it may not actually look like what you have. Okay, so that's just friendly advice from Bruce to you. Just realize that it may not pan out to be exactly what you see, but it's equivalent. But you're probably used to that by now, that there are lots of different forms of these. All right.
Bruce, was that all the bad news, or was there the good news in there? And it was all logs?
No, remember, the good news was we didn't have we didn't have to do any more algebra.
Gotcha. Yeah, no, that was good. I just wasn't sure. I was wondering sure if it was coming.
Oh, you wanted the magic bullet good news. You wanted the, oh, but yeah, this isn't actually how we really do it. Let me show you the fast way. Right? That's what you were waiting for, because I know that happens a lot in calculus. There is no magic bullet.
Yeah.
There is no
some kind of good news. Yeah.
No, the good news is once you're done with the algebra, the calculus is easy. That's the good news. All right, so let's try another one. Let me show you another one, because I want to show you another one that's got a repeated factor. Because I did show you that last time, but it was still such a brand new process that I think I probably lost most of you after about step number 2 anyway. So let's try this one. Let's go with the integral of 2x plus 3 over x cubed minus 3x squared. All right, so again, it's not terrible looking, but it's one that partial fractions is going to be the way that we have to tackle. Just going to remind you real fast. Anytime you have one of these, always look for U sub. Always. Always look and see if the top is the derivative of the bottom or related to it, because that will save you all sorts of heartache. You can just do a U equals on the bottom and get a natural log and be done. Okay, so always keep your eye out for that. So what I do, I'll look at this bottom and I'll differentiate it. It's 3x squared minus 6x. And I look at the top and I go, yeah, no, that's not even close. So this is one where U sub won't work. So we are going to use partial fractions. So let's start factoring that denominator. So x cubed minus 3x squared. This one's actually a real quick factoring. There's a common factor of x squared. And then the other factor is x minus 3. All right, cool. So here then is going to be how we break this fraction down. So the 2x plus 3 over x cubed minus 3x squared is going to equal. All right, so I've got a factor of x. So I'll put x on the bottom. It's repeated, right? That's x squared, which tells me there's another one with an x squared on the bottom. And then there's a factor of x minus 3. That's going to be my third one. So this one also has 3 pieces, but they're going to be x squared, and x minus 3. So when you have a repeated root, repeated factor, you need to have as many fractions as that highest power. And each of those fractions has a different power of that factor. So had this been x cubed, it would have been an x squared, and another one with an x cubed. And then the x minus 3. All right, and so now I need to put tops on these. Well, x is a linear factor, so that just gets a. X squared. I know it's squared, but it's still a linear factor, so it just gets b. And then this last guy, that x minus 3, it's linear, so it gets a c. All right, so that's a over x plus b over x squared plus c over x minus 3. All right, so that's what that one looks like broken apart. So repeated factors, they show up more than once. All right, so let's build this back up. All right, so we're going to have the top here is 2x plus 3. 2x plus 3 is going to equal. Now the a is going to need an x and an x minus 3. So when we combine it, it's a times x minus 3. The b is only going to need x minus 3. And the c is going to need x squared. Because that common denominator is x squared times x minus 3. So I'm just introducing the missing pieces to each of those. So this is the thing that we're going to plug values in so we can find a, b, and c. All right, so before I do that, any questions on where we are?
Yeah, why did the x go away? Why wouldn't you multiply x and x squared?
Okay, so why did the x go away where?
On like b, wouldn't it be x times x minus 3?
No, it's actually just going to be x minus 3, because think about if you were to build this up, I want to get x squared times x minus 3, I would need to multiply the bottom by x minus 3 to get this denominator. So that's all that it's going to get on top,
Okay, that makes sense.
right? The last one needs the x squared, and this one's missing an x and an x minus 3. So that's where all these are coming from, is just the building it up. So I like to just think of it as what factors are missing. When I factored this, I look at these bottoms and go, which factors are missing? And that's what I attach to the letters. So is that better, Alexi?
Yeah.
Yep, okay, cool.
Bruce, you lost me around the b. Isn't x squared non-linear? So wouldn't that be a bx? Or
Okay. Yes,
I
x
missed
squared
that
is
part.
not linear. X squared is not linear, but the factor it came from, the factor is x. It's just repeated, right? So that factor is linear. So since the factor itself is linear, it's still just a b on top.
Okay, so say if it was +1 like the last one, that's why it's not. Okay, the factors aren't. I see.
Because this
Thanks.
this is a repeat of a factor, right? Like the x squared plus 1 was its own factor in the previous example. This one, the x squared, it's a repeat of the factor x. So it's a repeat of a linear factor. And that's why there's just the b on top. Well, that's a good question. And that's something that, you want some good news on that? I'll definitely give you some good news on that. Let's say you went with linear on top there. So you called it a bx plus c. It's totally still going to work out. You'll find that that value on the x is 0. So the good news is that's never going to be a mistake. The bad news is it's going to increase the amount of work you have to do when you solve your system, because you're putting in a variable you don't need. So worst case scenario, you make that thing linear and it turns out that the linear part doesn't matter. But save yourself some time. Recognize that it's actually just a repeated linear factor, so I can just go with a constant on top. All right, awesome questions. Any else? Any other ones? But it's good to get these things out so that we're comfortable with it going forward. So I appreciate those questions. All right, so now we get to start plugging in numbers. So what numbers do you want to use? Give me a good one to start with.
0.
Oh, thank you. I love 0. First of all, I just love plugging in 0, but also it's going to make one of these denominators 0, which is always good. So let's plug in x equals 0. All right, now, unlike the last one, remember the last one, the top of the fraction originally was 1, so it was always the same. This one, since the top of this fraction is variable, we have to plug in these numbers on that side as well. So if I plug 0 in here, I'm going to get 3. Right? 2 times 0 plus 3. The part with the a is going to go away. With the b, I'm going to get b times -3. And the c, that goes away as well. So I get 3 equals -3b, which is a really fast b equals -1. Yes. All right, so x equals 0 was a great choice. All right, give me another choice. What's another good number to plug in? Yeah, okay, so in my mind, I was saying, please say 3, please say 3, please say 3. So thank you, Lexi. And I said, let's go with 3. 3 is another awesome choice because it makes the x minus 3 is 0. So if I put that in, I get 2 times 3 is 6, plus 3 is 9. 9 equals, I'm going to get 0a plus 0b plus 9c. So plugging in 3 gives us 9 equals 9c, or c equals 1. Awesome. All right. So now we need to plug in something else. And at this point, we are out of good choices, right? If you come back and you look at these originals, in terms of values that make these factors 0, well, 0 and 3 were our 2 options. So let's pick something else. Anybody care?
Can we try -3?
We can.
Or would
rather
what? Okay, 1.
I would rather not use -3 because then I know for sure I'm going to have negatives. I think 1 is a really good choice, but I'm actually going to choose something different. I'm going to choose 4. Can anybody see why I'm going to use 4 instead of 1? And it's definitely not because Alexi said 1, right? But yeah, if you look at what happens when I plug in 4 into these factors versus 1, it's going to make all these factors positive, right? 4 minus 3 is going to be a positive 1. As opposed to if I plug in 1, I'm going to get negatives. And just so you guys know, I have some issues with negatives. They've been kind of bad to me in the past. Sometime I'll tell you my story about my first grad school program and what happened with a minus sign. But negatives cause me trouble. I routinely make mistakes when I have negative numbers. So I try to avoid them as much as possible, which is why I'm going to go with x equal 4. Now, you want to go with x equal 1, go for it. You want to plug it, Suzanne's at -3, go for it. It doesn't matter. I just know the fewer negatives I have, the better. So I'm going to plug in 4. We're still going to get the same value no matter what we do. So if I plug in 4, 2 times 4 is 8 plus 3 is 11. So 11 equals. I'm going to get 4 times 1, so 4a. I'm going to get 1 times b, so b. And then I'm going to get 4 squared times c, so 16c. But now I know the values of b and c, so I'll put those in. So b is -1, c was +1. So this is pretty fast again. If I combine things, move stuff around, I get -4 equals 4a, or a equals -1. Right. So plug in whatever you want. I just saw that 4 was going to be pretty fast and easy and keep me from dealing with negatives. All right, so here we go. Now we can change this integral into an integral with these pieces. So we're going to have a over x, so -1 over x, plus b over x squared, so -1 over x squared, plus c over x -1, or sorry, -3, so 1 over x -3. So I literally just put those a, b, and c values in there. All right, so again, think about this at this point. we haven't done a touch of calculus. Everything has been algebra. But again, good news, bad news. Good news, we're done with algebra. Bad news, well, we're not quite done. But now we get to integrate, and this is going to be quick. All right, so minus 1 over x. That's negative natural log of x. Minus 1 over x squared. We've got to use the power rule. But that's equal to 1 over x. And x to the minus 1. And then the 1 over x minus 3, that gives me another natural log. We get natural log of x minus 3. And then, of course, our lovely plus c. But now we can put a box around it, because there's our antiderivative of 2x plus 3 over x cubed minus 3x squared. All right, so there was another one. And just compare this to the one we did before. I think, to me, this one went faster. Partially, that's because we only had 3 variables we had to find. Okay? We only had A, B, and C here as opposed to A, B, C, and D. But I also think it went faster because we're starting to see the process. We're starting to see how this goes. And I think the more of these you do yourself, you'll see the same, that it speeds up. Okay, so how are we feeling about this one? Questions about this example? None, we're feeling better. Okay, so I just looked at the clock and I see that we've got like 7 more minutes, and 7 more minutes is definitely not enough to do an entire one. But what I want to do with this next one is just have you set this thing up, right? To get it to the point where we break it down into what the fractions look like, just for the practice. All right, so let's go with this guy. Let's break this one apart. So we'll make the top be x, and let's go with the bottom being x to the 6th plus 4x to the 4th plus x squared. Make this 4x squared. All right, so we got x over x to the 6th plus 4x to the 4th plus 4x squared. All right, so step number 1 is let's factor this denominator. So hopefully you guys all see that there's an x squared in common. So let's pull out that greatest common factor. So we've got x squared times x to the 4th plus 4x squared plus 4. All right. So this next piece, x to the 4th plus 4x squared plus 4, that also factors. It's x squared plus 2 times x squared plus 2. This is one of those that's in what we call quadratic form.
Notice that the powers are getting cut in half. Right? So x to the fourth, x squared. So it actually factors very much like what you're used to. You could even put like a u equals x squared or something like that to turn it into a quadratic. There's its factoring. And the x squared plus 2's, those don't factor down any further. All right, so we're done with our factoring. So now let's split this thing apart. Let's see what this fraction would look like, or what fractions we're going to need. So x squared, that's a linear that's being repeated. So we need to have an over x and an over x squared. Okay, then I've got x plus 2, or x squared plus 2. That's also being repeated. So I'm going to need 2 of those. Well, what they're going to look like are x squared plus 2 for one of them, and then x squared plus 2 squared for the next. That might be a little bit easier to see why that is if I were to write it like that. But there's my factor being repeated. It's going to have to show up as many times as the repetition, so it's going to show up twice with the power. All right, so now what's going to go on top of these? Well, the x is linear, so it gets a constant. X squared is a linear factor, repeated, but it's a linear factor, so it also gets a constant. X squared plus 2, since that's quadratic, its top is going to be linear. So cx plus d. And then the other one, x squared plus 2 squared, that's also a quadratic factor, so it also gets a linear. So we'll call it ex plus f. Okay, so check this out. This one now has 6 variables we're solving. Yeah. So this one, we're going to have to plug in 6 different numbers to end up finding A, B, C, D, E, and F. So the more complex the denominator, the more variables you're going to get. And actually kind of makes sense. And in fact, notice the degree here, degree 6. Turns out there are 6 unknowns. Go back and look at the other 2. The first one we looked at was x to the 4th minus 1, so degree 4. There were 4 unknowns that we had to find. The most recent one, the x cubed minus 3x squared, was degree 3, and there were 3 unknowns that we had to find. It's not coincidence. That's always going to be the case, that the number of unknowns when we split it apart is equal to the degree. All right, so these are the pieces. So if we were to put this together so that we could get the equation that we're going to use for let's mark in the right spot so I can avoid it. So here's what the equation is going to look like that we're going to plug numbers into. We're going to have x equals, because the top was x. All right, so we're going to get a times x squared plus 2 squared. These are the missing factors in the denominator for a. B is going to get b times x squared plus 2 squared. The cx plus d is going to get times x squared plus 2. And then the ex plus f is going to get times x squared. So all that stuff on the right of the equal sign, not big long string. That's the top of this fraction when it's all put together. And then I set that equal to the top over here. All right, but I think this is where I'm going to stop this one, because now it's just a matter of plugging in numbers. In terms of good choices, there's really only one good choice. And that's x equals 0. Because that's the only thing that makes any of these bottoms 0. So when it comes down to it, I would definitely choose x equals 0, right? Because like if you plug in x equals 0, you're going to get 0 equals, well, a times 0, b times 2 squared, so 4b. And then you're going to get 0 from all this stuff and 0 from all the rest. So, oh, that one was quick. B is equal to 0. Cool. And actually, now that I know b is 0, I would immediately just cross that off and cross that off, because it's not even there. It'll make it so that it's a little bit easier for us. But now it's just a matter of choosing x's. So like, well, I'll do one more for you. Let's plug in 1. So if I plug in 1, I'm going to get 1 equals, well, let's see, 1 plus 2 is 3, squared is 9, times 1 is 9, so 9a. Plug in 1 over here, I get c plus d times 1 times 3, so 3c plus 3d. And then when I plug in 1 over here, I get e plus f. So whatever these numbers are, 9a plus 3c plus 3d plus e plus f equals 1. Okay, well, I pick 4 more numbers to plug in, put them in. I'm going to get 4 more equations. That's a system of equations. 5 equations, 5 unknowns. This is why I'm not actually going to do this whole one. Best way to solve that is with a matrix. Put all your stuff in coefficients, do the good old reduced row echelon form stuff. I'm not going to go into that, but we have to solve that system. So you can see that these can get really gnarly, really fast. And yep, the matrices are everywhere. And if you don't like matrices right now, don't plan on taking linear algebra. Math in our sequence math 203, which is next year, because it's all matrices, everything to do with matrices. So yeah, again, pre-calc, there's a reason we teach you stuff in pre-calc, so you can use it in calculus. All right, anyway, so these can get really big, really ugly, really fast. Which is why, obviously, on an exam or something, I'm not going to give you something like this, because it's unrealistic to try to do. Like, this one problem is going to take you at least half an hour, which would leave you, no time for anything else on the exam. But anyway. All right, so there's partial fractions, without mistakes, and one mistake anywhere, it's over. So go slow. This is definitely a slow step. All right, but partial fractions, take it for what it is. It's a technique for solving these things, or for breaking apart rational expressions and turning them into things that are pretty easy to integrate. All right, so real quick before we go, just want to remind you that there is a quiz next time. It is going to happen. That quiz is going to be on sections 2.9 through 3.2. So Quiz Friday, 2.9 through 3.2. So those topics, 2.9 is the hyperbolic trig functions. 3.1 is integration by parts, and 3.2 is the trig integrals. So that's what's going to be on this quiz. Usual setup, quiz will be open and ready at 8:30. We'll start in here at 9:10, and we'll talk about what we call improper integrals. They just involve infinity. So anyway, so with that, hey, you guys have an awesome couple days, and I will see everybody on Friday. Aloha.